Hello everyone. In this video we're going to talk first we're going to make a review about data analytics, and then we're going to discuss a little bit of dimensionality reduction, which is an important technique when we have big data, especially structured data, and maybe you want to drop some variables like reduce the dimensions. So let's learn a little bit of a principal component analysis. Okay, so data analytics, it's just the science of analyzing raw data and make good decisions. So we're taking here data to action. That's the main idea. So these are the steps in general. We have like a data requirement. Typically it's like a business problem that we want to answer or solve. Then we start our data collection. There are multiple ways to perform this data collection. We process data, we transfer data, we clean our data, of course. This part is critical, the data analysis. So today we're going to discuss in this video the different types of data analysis. And at the end, we have data interpretation, and that's when we make decisions. So let's amplify some of these steps. The first one, the data collection. So it involves multiple sources. Remember the variety in our data. So we may have surveys, structured methods to collect data, sensor data. So we might have some sensors collecting data in our company, in our system. Transactional data, sales, inventories, all the information that typically even a small company is going to store. Web scraping, so extracting data from different websites and APIs. So same idea. So it's like applications that allow us to download some information. So there's an exchange of information. Data cleaning is really important, especially when we're talking about big data. So you gotta make sure that your data is clean, that you don't have problems like with duplicates, that we don't have errors. Or the idea here is we need to check for missing values. And the way we deal with missing values, it depends on the problem, because the solution can be as simple as just removing the incomplete records. But in some cases, that will be a problem, because if you remove, maybe you're gonna decrease your database to like less than the like 50% of the original database. So that's not a great idea in that case. So it depends. You gotta be careful. There are some models even to kind of like find or to fill the missing values. So there are some like regression models, and there are some more basic models such as like to compute the mean value and to substitute using the mean value, so to avoid filling with like problematic data. All right, outlier detection. It's important to estimate anomalies in my data. So all of these steps are relevant here in the data cleaning stage. Visualization, when you're making decisions, even before creating models, visualizations are important to understand our data. And also at the end of the process, when you want to sell, when you want to, like people inside your organization to buy your idea, your model, or your analysis, plots and visualizations are really important to sell the story. So you need to learn, like how to create like good charts, heat maps, dashboards, and this is what's really important here: the storytelling with data. So this is how it looks, storytelling. So when we have our data collection, it's like a little bit messy, unorganized data. So then we start preparing our data, organize our data. So we can start creating some plots, basic plots. Like if you're using R, you can use like R-based plots. If you're using Python, then you're going to use like maybe matplotlib here, so something very simple. But then as your analysis progresses and you start finding like interesting results, and you start like proposing like interesting ideas, so now you need to create a story, because that's like what decision makers are going to buy, the story. They don't care about the code, like how fancy is the code, how long is the code. At the end, what really matters is how you sell that story. So it is important to have a good story to offer. So that data storytelling is a big thing in the process. Okay, so what are the data analysis studies, the data analysis types that you need to remember? and there is like a hierarchy. So we're going from the most basic study to the most like complex, let's say. It doesn't mean that there is one study that is more important than the others. It just depends what you need. So this is why you need to understand that this different study types, because once you know like the difference between them, you will be able to pick the right one in your context. Okay, so the most basic study is descriptive, followed by exploratory data analysis or EDA. I'm going in detail in the next slides. Then we have inferential, which is inferential analysis is a generalization of your results. Predictive models. This pretty much I believe that most of you that are like doing the master in data science, I'm pretty sure that predictive models is what you're trying to like that's like the most appealing area in data science. We have also causal analysis and mechanistic study, which we're not going to study the mechanistic ones. All right. So let's continue. Now with the first one, the descriptive analysis is the most basic study that you can do. So here, what we will have, mainly we will compute like number of, for example, if we have a census, here, like, number of people in a country, by gender, also like the age, average age. So here you have some metrics. Maybe some tables, right? But in descriptive analysis, it's pretty much about just metrics and tables, and we don't have like plots or insights. So it's more about just metrics, really. This is number one. Number two, and I believe this should be always your first step, an EDA, an exploratory data analysis. A descriptive analysis, it's too basic for you. You should always begin with exploratory data analysis. So here, you really understand your data. You need to plot your data. You need to start analyzing, comparing your variables, like checking, like, okay, what is the impact of x1 and x2 in the y variable, and things like that. You need to measure correlations. You need to create some heat maps, analyze time series if that's the case. So here we need that exploration. This is visualization driven for sure. We need a lot of plots during this stage, and at the end, in the EDA, we generate hypotheses. We cannot confirm it yet, but we can generate some hypotheses. Like sales are increasing in this area, or this segment of these customers are decreasing the number of units that are buying from us, and things like that. So the EDA, again, it's really important in any data analysis. Even if you're doing something more complex, you always need an EDA. And I'm pretty sure that in companies, like at least 95% of the times that you're gonna perform a data analysis, it will be an EDA. Always. Like every month. Even if they don't have an analytics area, they need to do a basic EDA. Like maybe see some plot, visualize the evolution of some variables, sales, some key metrics. So the third level of data analysis is inferential analysis. So in this one, we try to draw conclusions from a sample, and we try to generalize. So let's say that we wanna check like how satisfied are our customers with the service that we offer. So we can conduct a survey, maybe to 1,000 customers. That's our sample. So based on the sample in these 1,000 customers, we can make an inference, about our whole population of customers, and see how satisfied they are. So a common example is election polling. Now that we are in the U.S. presidential election, every single week you will see new polls showing the two candidates. Oh, I think that, there are more candidates, but the two big candidates. So that's an inferential analysis, because with a sample, they are trying to generalize what the potential voters are gonna pick. Now, who's gonna pick? Okay. Now let's get to the fourth data analysis type, it's the predictive analysis. As I told you, I'm pretty sure that this is the motivation of most of you when you're joining these courses. So in the predictive analysis, the idea is to predict one or more variables. So typically we talk about one variable, but in general they can have multiple outputs. So typically we call that variable y, the dependent variable, right? So the most popular predictive models, I would say they are the regression analysis and classification. In both cases, you want to predict a y variable using x variables. Now, what's the difference? The difference is in regression, our y, our dependent variable, is numerical. It's a numerical variable. In the case of classification, it's a categorical variable. That's the big difference. Now, let's see some examples. In the case of regression, let's say you want to predict a house price, like the price of apartments or houses. You want to create a model for that. So your y variable is the price. It's a numerical variable, and then you will have, of course, some predictive variables such as, let's say, the size of the house or the apartment, whether it's used or new, like where it's located, and all that information is going to help you to make the prediction. Again, in the regression, y it's numerical. Now in the case of the classification, y is categorical. Some examples, if we're talking about online banking, so y can be like whether a transaction is fraud or not. So that's the possible values, like an okay transaction or a fraudulent transaction. So that's a classification because you want to predict whether a transaction belongs to the first class or the second one. Using, of course, some predictors. So x1 may be like the amount of the transaction, x2 can be like if the transaction was like online, or maybe it was in a physical store, and you can keep adding more variables into your analysis. Also, if you're talking about like in medicine, like some applications, there is like prediction of some diseases. So the variable is whether the patient has a specific disease or not. So that's a categorical variable right there. These are not the only predictive models. You can also have time series. Those are really important for companies when they want to predict, like, sales, the amount of sales that they're going to have in the next periods. So they use time series analysis to make predictions. Causal analysis, this is the fifth level. They require different tools than the predictive models. In the predictive models, we can use correlation to make predictions, but the causal analysis is different. Here, you have full certainty that an X is causing an impact on the F variable. So there is a cause and effect relationship between X and the dependent variable. So here in the causal analysis, you have full certainty about this relationship. The standard tool, or the most used tool here, is the design of experiments. I think that is a course that you should take. I think it's part of the program. I'm not familiar, but I think I have heard it before. Design of experiments in our program. Okay, so it is important to make a distinction between causality and correlation. So in causality, implies that one event is the result of the occurrence of another event. So it's the full certainty that X causes Y. But in correlation, it doesn't mean causation. It's just like, okay, they are related, but not necessarily one is causing the other. So in other words, if you have causality, there is correlation, but if you have correlation, there is no causality. I mean, you don't have certainty if there is causality. You gotta be careful with confounded variables, which are variables that might influence both the independent and the dependent variable. Let me show you a quick example here. So imagine that we're in summer and the weather is really hot. So during that time, maybe the consumption of ice cream, cold drinks in general is going to increase, right? The sales are going to increase during those months. At the same time, like sunburn or even the sales of some products, for going to the beach or to the pool, they are going to increase their sales too. So there may be some correlation between the ice cream sales and these products and these problems. But that doesn't mean that because the sales of the ice cream are increasing, and then that's gonna cause more sunburns. That's not true. They are correlated, but one is not causing the other. So there may be a confounding variable here. Actually, if you don't see this variable into your analysis, then you might think that the causation is here, but actually this is just correlation. The causation is here. It's because of the weather. So this looks trivial, but it's not. In real life, you will see a lot of mistakes, even in academia. There are a lot of papers where they assume that a regression model or classification model, they assume that model is like a causal analysis, and it's not. All right. Now, the type of model that I want to mention in this video that are more related to our class and to big data is dimensionality reduction. So the idea here is that in some cases we have too many variables, and that's a problem, for processing, for storage, for visualization too. So if you want to reduce the number of variables, then you need to perform some dimensionality reduction. So there are multiple techniques. There are like two big categories: filter selection and filter extraction. What's the difference? In filter selection, maybe you have, I would say, like 1,000 variables, x1, x2, up to x1000. So filter selection means that you're going to take a subset of those variables. Like, let's say that at the end we end up with 30 variables here, just 10 in total. So in filter selection, the variables in your subset are original variables. So they are the same variables that were in your original data set. You just remove some variables that were not adding value. But again, in filter selection, at the end, we are using some of the original variables. But filter extraction is different. In filter extraction, you take the original variables and you transform them. You transform those variables. That means that you combine them. So you can combine, let's say, x1, x3, x4, x10 in a single variable. You can create like a linear combination or even nonlinear relationships. So you create new variables, and that's called filter extraction in general. So that's the difference. Filter selection, you keep the original variables, you just reduce the number of them. But in filter selection, you transform those variables, you can combine them. Today, we're going to talk about one technique which is quite popular. The name is PCA, Principal Component Analysis. Now, why is important dimensionality reduction? What are the benefits? Well, when you have high dimensional data, that means a lot of variables, and you want to decrease that number of variables, so you might have the problem that is called the cost of dimensionality, and maybe you're having issues when when you're training a model. So it's important to here it makes sense to apply a technique to reduce the dimensionality. Data visualization, we're limited. So typically in a plot we can see like 2 dimensions, 3 dimensions, no more than that. So I mean, there are some tricks, of course. You can keep adding variables, maybe using colors, some shapes, things like that, but in general we're limited, right? So if you have 100 variables or more, like how you're gonna visualize all of that? Maybe you are gonna create some pair plots, but you're leaving a lot of information outside the plot. Computational efficiency. Sometimes your codes, they take a lot of time to run. So maybe it's time to do some dimensionality reduction in order to speed up the process. Okay, so in PCA, Principal Component Analysis, is a linear technique that transforms the variables. So the PCA is going to create what we call principal components. Those are our transformations. So PC1 is the principal component number 1. So it's the one that captures most of the variance in the data. So here when you talk about most variance, means like it explains most of your data. That's the idea. So you keep adding principal components, right, until you can explain like most of your data. When you, in general, for any method to reduce dimensionality, you're going to lose some information. That's normal, of course. That's a sacrifice that you're doing. You're decreasing the number of dimensions, the number of variables, but you're going to lose some information, right? But the idea is to minimize that loss. Okay, let's do an example. Let's go to Python, and I'm going to show you like how to use PCA using Python, scikit-learn. The purpose of this analysis is to make a visualization to analyze our problem. So let me give you, let's go to Colab. So right now I'm assuming that most of you have used Colab before, that you know how to use Python. If that's not the case, please let me know. Just send me an email or in the forums in our discussions. Just let me know, and I can add more videos, give you access to I have another class, but I'm teaching that, R, Python, so yeah, that helps. I can give you access if you need that, or even I can add more review videos here. All right, so this is Colab. You can just Google it, Colab. You log in with a Gmail account here in Colab. And this is a notebook. In the notebook, you can add code and text. By the way, Colab can be used in general to code using Python or even R. Okay, so first step, what I'm doing here is just defining our libraries. I'm importing the library, so I have pandas as PD. This is an alias. Pandas is a Python library to manipulate data, to transform our data. Seaborn is to visualize data, and the alias is SNS. By the way, this is arbitrary, but this is a standard. Typically, pandas, everyone is going to call it PD, but I can change the name if I want. I can call pandas as DR because I'm Daniel Romero. So, but again, I can do it, but it doesn't look good. If you do that, it's going to be weird. If you change like the alias for pandas, that's weird. Okay. Seaborn, NumPy is for like linear algebra. It has some methods. Scikit-learn is very useful for machine learning, for regression analysis, classification, clustering techniques. I think even time series and dimensionality reduction. So here I'm bringing three things: the dataset. This is for the pre-processing because we need to standardize our data, and then here we have the PCA. Okay, so I run these libraries here. And let's get started. I'm going to bring the data, I'm going to explain it to you. So this is a medical dataset. It's for cancer, breast cancer. It's from scikit-learn. You can visualize it. This is a dictionary. Okay, this is a dictionary. So the target, it has two values. 0 is if the tumor is malignant, and 1 if it's benign, right? That's the type. So it's a classification problem. It has two outputs in this case, and the outputs are categorical. Maybe you see 0 and 1, you might think, oh, that's a number. It's just the code. But actually, you can type instead of 0, you can call it like malignant, 1, the number 1, instead of the 1 you can use benign, and it's the same problem. So it's a categorical variable here. It's not a measurement, you're not counting. All right, and then we have like our data, we have 30 variables here. And what are the variables? We have different variables. In general, they are related to the geometry of the tumor. They are more like the area, the perimeter, the worst perimeter, like smoothness. There are different metrics related to the shape of the tumor. So let me show it to you. Maybe sometimes the dictionary is a little bit messy to understand. So I'm going to create a data frame because I'm pretty sure that most of you are more familiar with tables. So it's df. This is just a data frame. This is a random name. Then PD from pandas. I'm going to create a data frame. I'm going to use the data from. the artificial intelligence is suggesting everything. You can use it, I mean, it's correct. What it's suggesting is correct. So the data is going to be cancer data. From the dictionary cancer, the data, those are the variables, the X variables, and then the columns refer to the names. So that's in the dictionary, it's under the future names. So it's working, it's suggesting correctly. So let me show you the final result, how it looks. So this is our data frame. Each column represents an independent variable. So x1 is the mean radius, x2 the mean texture, mean perimeter, mean area, mean smoothness, mean compactness, and it goes on until the last one. So that's our data. We need to standardize our data. Please notice that the scale is different. So for example, the mean radius, the values are 17, 20, but then we have the mean area is like 1000, 1300, so they are in different scales. And look at the mean smoothness, it's lower than 1. So we want to standardize our data. Let's do that. So we load the standard scalar that we define at the beginning, and then the scalar, we fill it with, we provide our data frame, our data, our X variables, and it's gonna scale the data, and then we store that information. The X scale, let me show it to you. It's just our 30 variables, but standardized. This is the distribution of our variables. Please notice that they are between -3 and 3, most of them. So now they are standard. We have standardized our data. So it's same as the original data set, original data frame, but now it's a standard. The mean value in this case, the mean is 0 for each variable, and the standard deviation is equal to 1. Okay. So now let's apply the principal component analysis, PCA. So I'm going to load the PCA. The main parameter is the number of components. So initially I'm going to create 30 components just for my analysis, because there are 30 variables. But of course we're gonna reduce that later, because as the idea, you don't want to keep the same number of components, like same as the original space, with 30 variables. That doesn't make sense, because you want to reduce the number of variables. So this is just to understand better what we're doing here. Okay. So I'm gonna compute the PCA with the scale data, with the standardized data, so let me store that here, XPCA. And now let me show you the interpretation of this. Let me show you what I'm getting to give you a better idea. So in the first two lines, we are computing PCA with our data, our standardized data. And now, at the end, I have a sum here. This is a cumulative sum of the explained variance. What is that? So let me show you. So this is for the first component. Remember, PCA1 or component number 1, principal component 1, is just a linear combination of our original variables. Remember, we had 30 variables, so using some of them, our method found that if you combine them, you can get one PCA, and that PCA is able to explain 44% of the variance of the original data. So this is like the percentage of the data that PCA represents. So this PCA, this single variable, this single linear combination can explain 44% of our original data. That's like the idea of the explained variance. Now, if instead of using a single PCA, you use two PCAs, like PCA1 and PCA2. So now it increases from 44% to 63%. And of course, if you keep adding more PCAs, so instead of 2, you use 3. So it's a cumulative sum. That's why I have come sum here. So now, if you use 3 PCAs, it's 72%. If you notice, of course, if you have like all of them like 30, it's 100%, but that doesn't make sense. But you can say that like beginning here in PCA number 7, you have like 90%. So that's reasonable. Instead of using 30 variables, if I have like 7 transformations of the original variables, like that's lower dimensionality, you know, like it's only 7 variables. Then, and you can explain almost, you know, like the original data set is 90% of your data. So it's a good deal. It's a good trade that you are doing here. If you wanna like increase a little bit more, you can do that. You can have like 10 variables, let's say, 10 variables, and again you will lose something, but 95% of your data, that's a good amount of data that you're explaining here. Okay, now for visualization purposes, that's the whole point of my example. I want to show you like how this method is useful for data visualization. So even though I'm losing information with only 2 PCAs, at least I want to evaluate, I want to visualize like my data and see if I can classify our data, if it's possible to kind of like make a difference between the benign tumor and the malignant tumor. This is part of my EDA, my exploratory data analysis. So for that purpose, I'm gonna copy this code. I'm gonna change name. We're gonna use only 2 PCAs because I want to visualize in a 2 dimensions plot, like normal plot, scatter plot. So that's why I'm gonna use only two PCAs. I used 30 at the beginning just to show you the interpretation of the explained variance. But now that you have an idea, so now I'm gonna visualize 63.7% of my, you know, like of the data. That's the explained variance. Okay, so this is for 2 components. I'm going to transform using the PCA that was trained. This is the transform data. This is PCA1 and PCA2 of the data. Now, what can we do with this? So let's plot PCA1 and PCA2 and see what we get. So using C1 as an SNS, let's create a scatter plot. For the X variable, I'm going to use PCA1. So when I want to use all rows from the first column, I'm typing 0 because remember that in Python, like the first column is 0. Same thing with the first row. So the second one is 1. For the Y variable, so here we're creating the scatter plot. So at the beginning, it doesn't say that much, right? It's like, okay, this is PCA1, PCA2. Now what? I don't see anything here. So let's add labels. Let's see, okay, remember that my original problem is that this is a classification problem when we want to try to classify if a tumor is malignant or benign, right? And I'm going to see in a plot if it's possible to classify them, right? So here with PCA, which is a dimensionality reduction technique, we're trying to visualize and see if that's possible. So then what I'm going to do is I'm going to add color to these dots, to the points of my plot, and to see like which of these tumors are malignant and which are benign, to see if a classification is possible. Again, remember, this is not 100% of the data. This is represents only like 60% of our data. It's an approximation. It's an approximation here. All right. So I'm gonna add the color. So from the data set, actually it's in the dictionary, the name is target. In the target, we have the zeros and 1. I show it at the beginning of the problem. So it's gonna the plot is gonna code for zeros, it's gonna give a color, and for the ones, it's gonna assign a different color. Right? Now you can see, remember, zeros are malignant, ones are benign. Please notice that when you see this plot, you might see, okay, it's possible to classify them, because if you notice, all the ones are to the left of the plot while the zeros are to the right. Maybe you will say, oh no, but there are some ones that are mixed with that's normal. I mean, you won't get like a perfect classification for all your problems. That would be ideal, but that's not the case. And in real life, data is complex. You won't see like perfect problems. Typically you will have errors, right? But if you notice, most of your data can be separated here, can be classified. So in this EDA, using PCA for dimensionality reduction, this plot at least give us a hope that we will find a model to be able to perform this classification. And you can try that later. I'm pretty sure that if you're taking a machine learning course at this point, you know the basics for classification models. So you can try a classification tree, random forest, or any other model, XGBoost, or even a neural network to perform the classification of this problem. All right, I'm gonna stop the video for now. So I hope you enjoy the dimensionality reduction techniques. They are really useful. PCA is for linear regression problems. I'm sorry, for regression problems. Linear regression is like the most well-known algorithm. For classification problems, logistic regression for sure is the most popular algorithm. Now in the case of dimensionality reduction, PCA is the standard. In clustering, K-means for sure is the most popular algorithm. Okay, I'm gonna stop the video. I'll see you in the next lecture.